That's the table. The block goes off. 1.2 meters is the horizontal distance. 0.8 is the vertical distance. Okay. It's launched horizontally. Applying the conservation of momentum, this is what you get. Remember that they stick together after the collision, doesn't it? And remains in a 3 kilogram block. So that's why the masses are added up. Then, of course, you have to change the 12 grams into kilograms. Initially, the big block was at rest. And then when I got there, I said, I cannot do this because there are two unknown quantities. Isn't it? So we have to, the velocity of the bullet and the final velocity with which it's launched. So you have to go back and look at the vertical component. The vertical component of the velocity is 0, A is 9.8. Vertical distance or displacement is 0.8. So use the king and find the time. You get the time as 0.4 seconds. Then what do you know about the horizontal velocity? It stays the same. There's only one equation that we can use, which is displacement is equal to velocity multiplied by time. So you go ahead, use that. And of course, that is the VF, isn't it? And you get that. Once you get it, take it back, go into that equation, plug it back into that, and find the initial velocity. (745 meters per second). Now, as you look at 42, you see that the 3 kilogram mass is initially at a height of 0.4 meter, isn't it? Yes. And it slides down the track, and there is no friction. And so surely you're thinking in terms of potential energy now. At the top it had potential energy, but just before it strikes the 1.4 kilogram mass, all of that becomes kinetic energy. So surely you know the initial velocity with which it is going to strike, isn't it? And from there you can apply the conservation of momentum and find whatever you have to. So potential energy at A is equal to kinetic energy at B, from which you can find the velocity with which it's going to strike. You get it as 2.8 meter per second. The second object is initially at rest. So now you can apply the conservation of momentum, and they do stick together, so their masses are added. And you can so find their speed after collision. It's 1.9 meter per second. Okay, this question has some differences. Number one, you see that the block is not at rest. It's moving in the opposite direction. Number two, after the collision, the block stops. And you're asked to find the kinetic energy of the bullet as it emerges from the block. Okay. So the bullet, 2,000 meters per second, because it's in kilometers. The block is moving at 4.2. Apply the conservation of momentum. This time they are not sticking together. Okay. But the block was at rest, right? That's why. And so you find the final speed of the bullet, and therefore you can find the kinetic energy. 1/2 times mass times the velocity squared. That will give you the kinetic energy as 512 joules. You have two blocks now with a spring in between. The blocks are pushed together. That means you're doing work, and the spring gets potential energy. The formula for elastic potential energy is 1/2 kx squared, isn't it? And then they let go, so they bounce back. Could you apply the conservation of momentum here? If so, what is the initial momentum? 0. Both of them are not moving, isn't it? Okay, so kind of situation like this. Initial momentum should be equal to final, and initial momentum is 0 because both are not moving. Therefore, 0 is equal to this. So you get the velocity is -3 And then you can find the kinetic energy of both of them is equal to 15 joules. And if that is the kinetic energy, surely that should have been the initial potential energy, because it's simply a matter of conservation of energy, isn't it? Because where did that total kinetic energy come from? It came from the potential energy of the spring. So that is... in this question, is the initial momentum zero? No, it is not, because it's already moving. And then it breaks up into three fragments. So one goes to the north, the other 30 degrees south of west, and the other south of east. Okay, so you have to make a diagram for this, kind of this way. And then I assume that it was initially moving along the y-axis. You could have taken it either way. So initially it was moving along, it was sliding along the y-axis, and then it broke into those three pieces. The idea here is that, of course, you have to use the conservation of momentum, but now you have to remember that you have to consider the conservation of momentum along the x and the y-axis, isn't it? Right? Or sometimes you may be able to do it just with one. So that's the 3 kilogram mass. Its momentum is 3 times its velocity. Now that is 4. Okay, how do you get 4 sine 30 times 2? Because each one has a vertical component which is 4 times sine 30. Both those 4 that I've shown has 4 sine. So twice that gives you that along the y. And plus the 9, you see that, times the mass. Is that clear enough? Okay. Therefore, the total y momentum is the sum of all those 3, which should be equal to the initial momentum along the y. And the initial momentum along the y was 3 times v, isn't it? But why the negative? Because from the diagram you can see that the 4 kilogram meter per second is downwards. It's opposite to the initial one. So if you take the initial one as positive, then that 4 is negative. That's why you have 5. And so you get the answer is 1.67 meter per second. So in this question, 450 kilograms per minute. Change it into per second. So that's the mass in 1 second. Thrust means force. And force is dP by dt. Just like torque is dL by dt. Right? Same thing. Force is dP by dt. That's the change in momentum in 1 second. And so you have the m by t already given. I've put the units there so you can see. And that gives you 39,000 newtons. So that's the initial direction. Their velocities. I broke it up into 2 components and then looked at the x components will cancel out, isn't it? Definitely. So you don't even have to look at the x because they cancel out. And the y, they get combined. And each one, what is each one now? Depending on how you have it, it's mass times velocity times sine 60. Anybody with me? Or I could say mass times velocity times cos 30. Both same. Okay, either sine 60 or cos 30. Both have the same value. All right. Multiplied by 2. Why? Because there are 2. That should be equal to total mass times the final velocity. Total mass is 500 grams, which is 0.5 kilograms. And they both move off at 26 meter per second. Direct question, because you have the angle given, you have to find alpha, which is the angular acceleration, which is d theta by dt. Just take the differential of that and plug in t as 2 seconds. You have the answer as negative 24 radian per second squared. That's the unit. Okay, let's go. You have the initial angular velocity, don't you? And you have the final, because it says it stops, comes to rest. You have the final, you have the time, and you are asked to find theta. And the most direct method of finding theta is this equation without having to find alpha. Average angular velocity multiplied by time. And you would get the answer and save 1 or 2 minutes. You could also find the angular acceleration, but then it's 2 steps. Until given the linear acceleration of the falling object, from which can't you find the angular acceleration? Can you relate alpha to A?
Yes.
Alpha is A divided by the radius. Just like angular velocity is linear velocity divided by radius. It's a similar connection. It is the same thing. Omega alpha is A by R. See? Look at the similarity between the two, and you should know how to connect these. So that's how you do that. So first find the angular acceleration. Then, what's the formula for torque? Alpha. Or R cross F, RF sine theta. This case, theta is 90. Torque has several formulas. This is one of them. Radius multiplied by the force. Force is mg, isn't it? Mg times the radius. Because the force is being acted upon here, mg, and that's the radius. That makes sense? Mg times r. That's how you get that. Okay. So you find that, and then use the other formula, I alpha. And then find the moment of inertia. 0.0392 kilogram meter squared. All right, in this question you have 4 particles. They're exactly similar at the vertices of a rectangle. So what I went ahead and did is, the moment of inertia of each one is mr squared, isn't it? It's symmetric about the axis, so just multiply it by 4 and you get the answer.
What is the last sentence talking about?
So that's the meter stick. You have particle 1 and 2. Find the torque due to each one. Aren't both trying to turn it clockwise? Yes, so you find the total, which is the net. Net torque is I alpha, and alpha is that divided by, and I stopped and I said, divide by I, what's I? Moment of inertia, and I don't know that, so go ahead and find the moment of inertia. Each one is a particle, so moment of inertia is mr squared. So add up their moment of inertias. As when you get that, plug it back there and find the answer. And then since you have to find A, go back to A is alpha by R. What? Alpha is A by R. Check that. It won't change the answer though, but that's a mistake. Alpha is A by R, isn't it? Yeah, I put, it won't change the answer, but I noticed it, not you. Okay. Alpha is A by R. So you get 11.53 meter per second squared. See, it happens. So in 53, the force is at an angle there. That's the pivot. So you see the component which is at right angles to the distance now. So you get F sine theta times R. The angle is 40 degrees. You have the force. Now, when a rod is rotating about one end, its moment of inertia is ml squared by 3. There are certain things that you have to know. About the center of gravity, ml squared by 12, isn't it? At one end, using the parallel axis theorem, it's ml squared by 3. You have to know the moment of inertia of a solid sphere, 2 by 5 mr squared. Hollow sphere, 2 by 3 mr squared. But the most important is the moment of inertia of a disk or a cylinder, which is mr squared by 2. Do not forget the by 2. Most people do. Moment of inertia of a particle, mr squared. Okay, so particle mr squared, disk or cylinder mr squared by 2, rod ml squared by 12, about the center. About the end is ml squared by 3. Solid sphere 2 by 5 mr squared, hollow 2 by 3. That's all you need to know about the moment of inertia. Okay, once you know the formula, find the moment of inertia here. It's in kilogram meter squared. Then put it back into tau is I alpha and find alpha. Get it in radians per second squared, 10.03. Therefore, this question is about the minute hand, and it takes how much? 1 hour. One rotation in 1 hour, so that's 2 pi radians in 3600 seconds. Therefore, omega is 2 pi by 3600, and the answer is pi by 1800 radians per second. All right, 55 is talking about angular momentum, and the formula for angular momentum is I omega, and I is mr squared because it's a particle here. Omega is v by r, isn't it? In circular motion. So you find the angular velocity, and then you have the moment of inertia, so put them together, you get the angular momentum. That is the unit of angular momentum. Kilogram meter squared per second. Okay, that's the diagram. Initial angular momentum is equal to final, and angular momentum is I omega. I is mr squared. That's why you see mr squared and omega and all that. And because they stick together and rotate, you can add, just like you add the masses in linear momentum, here you could add the moment of inertias. Now, I realize that mr squared is not going to get you there. So angular momentum is also r cross p. Anybody remembers that? Angular momentum is r cross p. That's the definition of r cross p. Angular momentum, in fact, r cross p. And you know that is rp sine theta. Isn't it? And if theta is 90, it's simply r times p. And p is linear momentum. That's how I get mv times r. Okay. Looked at what is given and then changed that. And then it's just the math. .17 radian per second is the final answer. The idea when you come to stability is that the vertical line drawn through the center of gravity should be inside the base. Again, the vertical line drawn through the center of gravity should be within the base. If it's outside, you're gone. And if you're looking for a limit, as in this case, then you would draw the diagram much better than I do, please. But something like this. Did you see that? The red arrow. I had to incline it a little bit. It's not vertical anymore. It is supposed to be vertical, and it's supposed to pass through that point because you're looking for the limit. Now, from that little triangle, can you tell me what tan theta is? Isn't tan theta this side divided by this side? Tan theta? So shouldn't it be radius divided by half of the height? Okay, let's see whether I put it that way. Tan theta is radius divided by half of the height. Yeah. Half of the height. Okay, h by 2. Therefore, theta would be tan inverse of r by h by 2. Wouldn't it be 2 on the top? Oh, that's not r squared. That's r times 2 by h. Okay. So that's the answer, 2r by h. I just noticed that I didn't take half of the height. Didn't you? So it's 2r by h. Okay, so that's 57. Two masses, there they are, mass. The distance between them is d, and you're asked to find the distance of a third mass from the smaller one, so that the net gravitational force would be 0. What do you mean by net gravitational force is 0? Immediately you have to consider that there is a 1 kilogram kept at that point. A 1 kilogram kept at that point. You see that? And don't you think that the two would be attracting it in opposite directions? And if the net force is to be 0, then their attractions must be equal. That's all. Their attractions must be equal. Okay, so that's the 1 kilogram that you imagine. And so the distance from the other one is d minus x, surely. Then the easier way is to take the square root. On both sides, cross multiply and find x in terms of d. 0.29 d. Okay. What do you mean by mechanical energy first? Mechanical energy, what do you mean? Mechanical energy is actually the sum of the potential and the kinetic energy. So you have to know that. Mechanical energy is the sum total. So you are given the mechanical energy and you're asked to find the kinetic energy. And it's about a satellite revolving around the Earth. For sure you know that the centripetal force is provided by the gravitational force, isn't it? So mv squared by r is equal to g, product of their masses, by distance squared. So you have that idea, and couple that with the idea of energy, as you're going to see. Okay, kinetic energy minus this is mechanical energy. And you're like, what didn't he just now say that mechanical energy is the sum of, and how come it's a negative? Because the maximum value of potential energy is 0, and that happens at infinite distance. The maximum value of potential energy, which is the second term, you see the second term there? The maximum value of potential energy is 0, and that happens at infinite distance from the Earth. That means all other points, potential energy is negative. Why is it negative? Because it's an attractive force. Any attractive force creates a negative potential energy. You need to know this even for semester 2. That's why there's a negative there. And I tried to give you a numerical example just for the fun of it. 5 minus 10 is negative 5. Surely everybody understands. And that also shows that the kinetic energy should be exactly equal to the negative of the mechanical energy. Watch. Isn't the kinetic energy equal to the negative mechanical energy? In that example, which I'm going to prove. I told you the force, centripetal force, is provided by the gravitational force. Take a look at that. What is that? That gives us mv squared is gmm by r squared. Isn't it? The r gets cancelled. Now compare. If mass times velocity squared is gmm by r, and kinetic energy is 1/2 mv squared. Isn't my example correct? Numerical example? I need to be thinking. I mean, the rest is for you to make out. I cannot, because look, I proved that this is equal to this, which is that one. So if I take this as 10, surely that should be 5. So we got the answer. How? What's the answer? to this question? What is the kinetic energy? Don't make it like a big joke. Come on, what is its kinetic energy? It should be 10 to the 12, but there is.
That is 10 times 10 to 11.
There's 10 times 10 to the 11, which is the answer. Because 10 times 10 to the 11 is 10 to the 12. Is it a floating object? Whenever an object floats, the weight of the floating object must be equal to the weight of fluid displaced by it. And what's the weight of fluid displaced? Volume times density times G. All right. So because it floats, weight is equal to the weight of fluid displaced, and volume can be written as area of cross-section times height. So you get the mass, G's cancel out, and H is M by A rho. The mass is given. The area is 300 times 80, and the density of seawater is 1020, so the height is 24.92 meters. Yeah, according to Bernoulli's principle, the total energies are constant. What are the three types of energy? Pressure, potential, and kinetic. Formula for pressure energy? Work done, PV. Kinetic, 1/2. Potential, and GH is a constant. Okay, that's not the format that you see it because you divide throughout by mass. Divide throughout by mass, and you see that this becomes pressure by density plus V squared by 2. Do you see this there? Plus GH is a constant. And if you are ever asked to do problems using Bernoulli's principle and the question says it's a horizontal pipe, then you need not consider the potential, isn't it? Now, coming back to this case, what is the pressure at point A? Point A is just at the surface. The pressure at point A is the atmospheric pressure. What is the pressure just outside the hole? Atmospheric pressure. You see that canceled out on both sides. Now let's talk about kinetic energy. It's a huge tank. Imagine it's a huge tank and it's a small hole. What does that tell you about the falling liquid surface? Is it going to fall fast or so? It's not moving, or it's moving rather very slowly. So the velocity is what? 0. Oh, so the pressure is atmospheric pressure. Velocity is almost 0. Now what's the next one? Potential energy. Okay. Let's measure potential energy from here. So that would be H, isn't it? Now at this point, the pressure is again atmospheric. The kinetic energy is of course there. And then what is the potential energy? None. So you see the left-hand side? What do you have on the left-hand side? I don't know if you've been listening. You have this, isn't it? Plus GH. Okay. And on this side you have the same atmospheric pressure, and you have 0 plus you have V squared over 2. Okay, this cancelled out. And so you get V squared is 2GH. Velocity square root 2GH. This is called Torricelli's theorem. I did this because when I was teaching I did not touch on that. This is another application of Bernoulli's principle. It's called Torricelli's theorem or Torricelli. How do you say it? Torricelli? I knew Italians. Okay. So that's it. Can't you use that directly to get the answer here? How? Like this. 2GH. Which is what he was trying to say, kinetic energy is equal to potential, but you know, you have to go there actually. So, all right, 61. 62. Oh, now we have Bernoulli's principle. Straight. Do you see the word horizontal pipe?
Yeah.
Yes. So first you will have to find the velocity using the equation of continuity. Didn't it say the area contracts to 1/3 of its? Okay, so that's why you have A1 and A1 by 3, which gives you the velocity as 15 meter per second. And now you can apply Bernoulli's principle. The potential energy term is missing because it's a horizontal pipe. Rearrange to make pressure the subject. That's what you're looking for. And do be careful when you calculate. There are lots of terms here. Okay. So you get 2.5 times 10 to the 5 pascals if you calculate carefully. There you go. Pressure inside and pressure outside. You take the difference in pressures, but it has to be in pascals, isn't it? So take the difference in pressure, multiplied by the area, change it into pascals. That's why you see the 101,325, because 1 ATM is that many pascals. And isn't that a huge force? No? It is a huge force. That brings us to 64. All right, the fire hose is at an angle of 30 degrees, shooting water out at 30 meters per second. What's the maximum height? That is easy. Maximum height, which component do you take here? The vertical component. And what do you know about the velocity at the highest point? 0. And A is negative 9.8, isn't it? Yeah, you take the vertical component, and that's 30 sine 30, 15. A is negative 9.8. You are looking for the vertical displacement. Use this formula. Substitute the numbers. Calculate. You get it as 11.47 meters. So now how many oscillations have completed in the second part? 5 oscillations have been completed. I hope you don't miss that. Sometimes somebody would take it as 4. So 5 oscillations have been completed. You have to find the displacement. And I think you can do it much faster than I did. Of course, you have to set up 2 equations. That's the first one. Everybody got that, isn't it? First one. And the second one, same initial displacement, 5. And then it's just a matter of solving for A. You can do it your way. You can divide the 2 equations, isn't it? Or get rid of the exponential because I don't like it. And then divide. See? Got rid of the exponential by using the natural log on the other side, then divide. And you have to be a little bit more careful on this one. And you would end up with the right answer if you are careful. 7.41 centimeter. That's how you change. And here, doesn't it say C is twice? Right? Okay. And so simply substitute that. In place of C, put 2F. Five by 9 is 0.55. Negative 12.26 degrees. Okay, so to do number 67, because it's constant pressure, you only have to do V1 by T1 is V2 by T2, isn't it? Will that work? Correct? All right, and then you have to know that 1 mole occupies 22.4 liters at 273 Kelvin and 1 ATM. Substitute, find a new volume. Take the difference between the new and the old. All right, in this question, pressure, volume, and temperature, all three change. Therefore, the only option is to use V1 by T1 is V2 by T2. But at the bottom, what's the pressure at the bottom?
It's
Atmospheric pressure plus,
density, gravity, constant.
yeah, liquid pressure, H rho G. It's atmospheric pressure plus H rho G. You see the H, the rho, and the G. P1. Volume, 4 by 3 pi r cube. Okay. I did one thing here, and it started out as a mistake, but then I noticed it doesn't matter because I took the radius as the, but it's a simple ratio. It'll equalize out because I write the same thing on the other side. Did everybody get that? Okay. So 288 should be in Kelvin. Kelvin. At the surface, the pressure is 10 to the 5. Just 1 atm, 10 to the 5. So many things cancel out, and again calculate carefully. You get 1.14 centimeter, which is not the radius again, it is the diameter, because I took it as that, right? Same thing. So 1.14 centimeter. Good time to teach. Okay, change name. Well, I just used gamma. I did not know what's on your formula sheet. I just used gamma. And how is gamma related to alpha? Yes. If it's cubical expansivity, it's 3 alpha. If it is area, it's 2 alpha. All right. So you given alpha. Alpha is the coefficient of linear expansion. In case you are struggling to find out what it is, that is it. The windshield increases by 5.8 centimeters squared when it gets hot. So when they manufacture the windshield, they have to have a provision for it to expand. And do they? Definitely. That's why it's held in place using rubber that can give way. Haven't you noticed that? If it was kept like that, rigidly attached, it will break on day one. When it expands, no space to expand. What is that? Safe flight. Whatever. Okay. 70. The piece of lead is the hot object, isn't it? And added to water. That is the cold one. So heat lost is equal to heat gained. And I have not written the formula, but you know that the formula is mc delta T. Mass times. The mass is 5. And I'm using the specific heat in calories per gram. And I made a mistake in the beginning. I noticed that. Did you see that it's 0.03? Somewhere along the line I noticed. Yeah, I did not change. You know why I did not change? Doesn't matter, because isn't it on both sides? If you change, wouldn't you do the same thing to both sides, which cancels out? Can you understand what I'm saying? So I just saved time.
What is the specific heat in calories per
1. Good question. 1 calorie per gram. Wait, that's how you get 4.2 joules per gram, 4,200 joules per kilogram. Did anybody understand? Let me say that again. 1 calorie per gram. And 1 calorie is 4.2 joules. Hello? Therefore, isn't it 4.2 joules per gram?
Yes.
And isn't it therefore 4,200 joules per kilogram? Yes. Very good. You got the connection. And you get, yeah, now I think I saw the 0.03. I corrected it. 33.84 degrees Celsius. That was number 70. Okay, the coin is dropped. It has potential energy, isn't it? It reaches a terminal velocity of 45 meters per second. That means a part of that potential energy was converted into kinetic. But the question says, and the rest of the energy is converted to heating the coin. So All you have to do is take the difference between the potential energy and the kinetic energy. Wouldn't you get the heat energy that's being used to heat it, right? Okay, that's the idea. So potential energy, take away the kinetic energy. Mass, 5 grams, has to be changed to kilograms. You get that, and then use mc delta T. Specific heat given. Amazing. Even with the small fall from a 300-meter building, a small object, its temperature went up by about 5 degrees Celsius. So think about I was thinking about the spacecraft that returns, cutting through the Earth's atmosphere, traveling kilometers down at a huge speed. Can you just imagine how much heat would be generated and what kind of a material we should have as an insulator so that the whole thing does not just explode, but still it has happened, right? Even that's why I stopped. I just suddenly remembered what kind of a death that would be as you come tumbling down and then explode in space. Is this what is given? The final volume is 1.5 times the initial. Is that correct? Because it says increases by 50%, isn't it? Right. So there it is, the adiabatic equation. Rearrange it. And that is 1 by 1.5. You've got to be careful there. Raised to 5 by 3. And that comes out to be 0.5. When you do 1 by 1.5 raised to 5 by 3, you get 0.5. So we got P2 by P1 as 0.5. That means P2 by P1 is 1 by 2, P2 is P1 by 2. So if the volume increases by 50%, the pressure is reduced by half. Did you see that? P1 by 2. Work over QH. Yes. 73. Efficiency is the ratio of work over QH. Work done. 40%. $74. First find the COP. $6.07. And I did tell you to expect numbers like 6, 7 and all that. That's why it's not called efficiency, right? Because if it was called efficiency, it would have been 607%, which is not possible. Okay. And then the other formula for COP. Yeah, because I wrote the whole formula and showed you that work is QH minus Q. Same thing. And then find the work. And to change from joules into kilocalories, you would divide by 4,200. Because 1 calorie is 4.2 joules. Since you want it in kilocalories, divide by 4,200. So you get it as 13 kilocalories. Okay, so change in entropy is always dQ by T. And dQ could either be positive or negative. Like if heat enters a system, it's positive, so the entropy will go up. If heat leaves a system, entropy goes down. So you have to remember that. Entropy. So you have to have that picture in your head. So, oh, is this losing heat? Its entropy is going down. It's negative. Change is negative. If it's gaining heat, it's positive. Okay, so you're asked to find the net change in entropy in this case. That is the formula for change in entropy. And here it goes from the molten state to the solid state, doesn't it? So it's again change of phase, mass times the latent heat, 0.1, that's 100 grams, times its latent heat. Therefore, that is the change in entropy during the phase change. Now, the question just says, what is the change in entropy of the lead? Separately, yeah. Yes, and then add all the entropies together. But in this case, I used the shortcut because if you are looking at the question, you know that the change of phase does not happen until 327 degrees Celsius. Look at the problem carefully. So first, what's going to happen is, it's at 600, isn't it? It has to cool down to 327, and then at 327 it changes phase, and then again from there it has to cool down to, anybody with me? 21. But I took a shortcut. You cannot do that all the time, but I could do it this time because they said the specific heat of both molten and solid lead are the same. Did you see that? So now I'm just going to say, all right, change in entropy as it cools from 600 to 21. Did you get what I said just now?
Only for this case.
Only for this case. If the specific heats were slightly different or they had given, then you would have to do it separately. Okay, so this case, that's what it is. So now the change in entropy during the cooling process, MC delta T. MC delta T, the temperature is in Celsius because it's a difference, but you keep it in Kelvin and take the difference. So now, see, now is the case when you have to take the average temperature. Remember that? Because it started from 600, but here you have to have it in Kelvin when you take the average. That's where students forget. Why? Because here they would keep it in Celsius. Doesn't matter. I've seen like 90% of the students forget to change it into Kelvin here just because you use those same numbers. And then you get the average, and then 128 joule per Kelvin, and the total, that has to be in, both have to be negative, isn't it? Both have to be negative, so heat removed, that's why it's negative. Added the negative to both, so the total is negative 132 joule per Kelvin. That brings us to the end of the semester. Thank you so much for your patience.